Okay, so at this point, we've got all of our forces drawn. And when I sum the forces on the big mass and I let down be the positive direction, the net force would equal capital M times A, meaning that the gravitational force, the weight of capital M, those are all subscripts, minus the tension force, and that's FT1, would equal capital M times A. When I sum the forces in the y direction on the little mass, it's going to accelerate. And if it accelerates upward, and I'll let upward be the positive direction, we would have Ft2 minus the gravitational force of the small mass. G and M are both subscripts there. And that would cause little m to accelerate. Then we have to now sum the torque on the disc, on the pulley. So when we sum the torque on the pulley, the mass of the pulley, will have an angular acceleration. It'll go from not moving to moving. So then we have to look at what forces are causing what. Well, if we know that it moves or should rotate counterclockwise, and we let counterclockwise be the positive direction, the force applied here, Ft1, is at a position that is equal to the radius, but Ft2 is opposing the rotation, and it's also at a position equal to the radius, and the whole thing accelerates. So now you have these equations for the motion of the system. Now notice that you have things like alpha and A. And if you're really careful, you'll remember that the linear acceleration A is related to alpha by R alpha equals A. So you can make a substitution there if needed. And this Ft1 is the same as this Ft1. And this Ft2 is the same as this Ft2. So we can make substitutions. And then it just becomes super fun algebra. Now, not all forces are applied perpendicular to the moment arm. So what do I mean by that? I mean that if here is a long thin rod and we apply a force straight up at the end of this rod and the pivot point of the rod is here, making this the length of the rod, then this force right here, the torque, would be the force, the magnitude of the force, whatever it is, times the moment arm length. The moment arm is the length of, or the thing that the force is being applied to, the moment arm. Now, instead, though, you have this same situation. Maybe we're looking overhead at a door, and here's the hinge, and here's the doorknob. And we apply a force directed this way now. So here's my force, but it's at some angle theta. Now, that means that part of this force is pushing straight into the door, perpendicular to the door. And some of this force is parallel to the door. So this is the piece that is perpendicular to the door, and this is the piece that is parallel to the door. Does the parallel to the door component cause it to swing? No. Does the perpendicular component cause it to swing or move, rotate? Yes. So torque really should be written as the force that's perpendicular to the moment arm times R. And in this case, it would be the opposite of the angle, so sine. So F sine theta times L, where L is still the length of our door, the width of our door.